So let's begin our conversation today on complex equilibrium with complex ions. And we're going to begin with this conversation of what Kf is. That's the formation constant. And hopefully this looks a little bit obvious that this would be just the opposite of a lot of what we've been doing. We've been doing dissociation and how many ions will live in a solution. And now we're looking at how much of a solid will form. We're looking in terms of these complex ions. And so then we can look at our Kf related to its dissociation constant as 1 over Kf will give us our Kd. And what we want to do first, when we're given two solutions that we're mixing together, is figure out what our limiting reagent is going to be. And I know it's obvious to you right now, if I have 0.025 and 1 molar, that the most I'm going to be able to make is probably this 0.025. But let's just really quick scratch that out and make sure that we're correct. So 2NO3. So if I have 0.025 molar of this, whoops, that's 2, not a 3. Then it's a 1-to-1 ratio. I have 0.025 of this. Now let's do our ammonia. Well, that just goes to ammonia. So now let's look at what they do in terms of the product. So we are going to have cu2 plus NH3. We're going to do our stoichiometry in a minute. To Cu NH3 4. So obviously I have 4 of these guys. So 1 molar divided by 4 is still larger than my 0.025, so I'm good there. But now let's figure out how we're going to pull some of these pieces together. So I only have this 0.025. So the most I can make on this side is the 0.025. And I'm going to start with 1 molar here. Now let's do this a little bit more formally. We're going to go 0.025. We're going to use all of that. So for argument's sake for now, we're going to say it's all going to go away. I'm starting with my 1 molar. I'm going to use 0.025. And I'm going to start with 0 here and gain 0.025. We're saying we've made the maximum amount. So this is going to give us amounts that we can make for our formation. So we'd get 0 here and 0.975 here, and then the 0.025 here. So that would be the first step. You want to write our equation in terms of what we're forming. So here's our complex ion, and we want what we're first starting to write to reflect that. So now we're going to take those numbers. I'm going to say we have starting with 0 here. Come back here, I have 0.975 of my ammonia to start with. So 0.975. This should look slightly familiar. And of my tetraamine copper 2 sulfate, I also have 0.025. I have 0.025 to start with. So we're going to go 0.025. So this will lose some amount X. This will gain some amount X. And this will lose some amount X. But what we're going to say is that this ion is really quite happy. So the vast majority of it will just stay. In fact, it'll be a small amount, so small that we can ignore this X. Let me do a different color. So we're going to ignore this X. X through it. And we're going to ignore this X because if 0.025 isn't going to change that much, then 0.975 sure isn't going to change that much. So now we have an end product of 0.025 and X and 0.975. Now notice this is going the opposite direction. This is going from my complex ion into my ions that would be in solution, right? So if I have the Kf, now I want to use my Kd because I'm going the opposite direction. So this would be dissociating the solid. I want to see how much of my Cu2 plus I have left when all is said and done. Cool. So let's just go ahead and write this out. Now this looks really similar to everything else that we've done. On the top, I'm going to have my 4, oops, not the 4 inside. How many times did I tell you guys not to do that? My NH3 to the 4th times my Cu2 plus. Now, unlike my KSP, I actually do take into account the part I have here of my complex ion. So that'll be the difference that you need to remember. So Cu, NH3, 4. And what you're actually going to see is a big part of this is because this is aqueous. Before, when we were doing that, we were doing with a solid, so the solid didn't count when we were doing our equilibrium equations, but this indeed is aqueous, so this is actually included. Remember, we're in molars, so we're not in a solid solution, or a solid state rather. So now let's go ahead and put in our x's. Our Cu2 plus is x. Our 0.975 for our ammonia. That's raised to a 4th power. And divided by concentration of our complex ion, which is 0.025. And we'll go ahead and write this in terms of the KD that I've already solved. So that's 2.08 times 10 to the negative 13. I just did that by taking the inverse of my Kf, my formation constant. And when all is said and done, I get, hopefully, something, if I didn't button push wrong, that this is 5.75 times 10 to the negative 17. So it really is a small amount, but it's still an amount. So this is just now kind of taking into account that when we say something completely dissociates, that in truth, there's still a little chunk left over. In this case, we're saying that we've created something, and this is the amount of ions that don't actually go into that complex ion. So this is our X. This is what is left over for our copper 2, and that gives us our final solution.